So welcome. My name is Coday. I'm going to take a little bit of a diversion from the typical talk about our software tools, and I'm going to talk a little bit about our CPU and the direction with which Intel is moving, what we care about when we talk to developers, and what are the key advantages of the CPU. Hopefully that will give you a little bit of background of how you can marry that with what the tools also provide as well. Okay. What do I do in my day job? I'm responsible for running a developer relations team in Europe, focused on visual computing. So that means games, graphics, predominantly consumer software. We talk to a lot of the consumer ISVs in Europe, Crytek, EA, DICE, you name it, we probably work with them. Okay, let's get going here. A little bit overview of the product and the features, then I'll talk about what programmers need to do to take advantage of the hardware, okay, and then kind of summarize it. Now, I know there's a wide diversity of people here, both in terms of how much they know about hardware, how much they know about software, so feel free to stop me and ask questions, and I'll try to answer them as we go. Okay, so how many people know the code name called Sandy Bridge? Okay? Okay, forget that name. We don't use that name anymore. We call it the second generation Intel Core processor family. Okay? Sandy Bridge refers to a family of processors, both on the desktop and the mobile notebooks, and those have all launched since January. Okay? This is the logo that you'll see. It's a little bit different than the previous logo, primarily by the fact that you see the chip line through the middle. Okay? Okay. It comes in our standard Core i3, i5, i7. i5 is better than i3, i7 is better than i5. Okay? Any questions? Pretty straightforward. Okay, so a little bit about how many different processors we launched. There were 4 new Core i3s, 12 new Core i5s, 12 new Core i7s, and 1 Extreme Edition processor. So interestingly, when we launched the Sandy Bridge family, or the second generation Core family, we did this across both desktop and notebook, and we launched it in the mainstream first. Now, if you've watched Intel for a number of years, historically, we actually launched the high-end desktop version first. And then about 9 months to a year later, we launched the mainstream. So Intel is shifting that dramatically, and now we're launching the mainstream first, and you'll see our high-end desktop will get launched more towards the end of this year. Okay? So that means when we launch the new processor family, it's mainstream first, volume, and then we follow up with the high-end. Okay? Okay, so a couple of key things about the second generation Core. It's on 32 nanometer. Okay? That allows us to use the same process that we used on the previous processor family. It gives us a level of stability rather than trying to change the architecture and the process at the same time. We only change one or the other on each generation. Okay? There's a couple of key features that we'll talk about. In the Turbo Boost technology, some of you may have been familiar with that in its earlier versions. Turbo Boost 2.0 is a big significant boost, to use the pun, and I'll describe how that works and what that means for programmers. The other really interesting thing is we integrated the GPU directly into the die of the CPU. So hidden underneath there is a CPU and a GPU fused together. They communicate and they talk together inside of the die. Okay? And that means graphics are much more capable at the mainstream platform. And I'll talk about that. And then also we have the Intel Advanced Vector Extension. How many people know SSE? Okay. We're now replacing, the next generation is no longer SSE 5, 6, 7, 8, 9. It starts with Advanced Vector Extension. So this is AVX 1.0. And we will have extension to that going forward. And I'll talk about the differences. Question? No? Okay. Okay, so this is what the processor looks like. You notice you see 4 cores across the middle top. big shared L3 cache. And then on the right, your left, you see a big huge part which is the processor graphics. Okay? And then on your right, you see a whole bunch of stuff. That is essentially the memory controller and most of what was formerly called the North Bridge. Okay? So most of that capability is integrated into the CPU now. Okay? A little bit more detail. Okay, that's the core. So, okay, who can identify where the L2 cache is? Just kidding. So you probably know, right?
No, yes. And it's not called any more shared L3 cache. It's not called LSD, last level cache.
So let's talk a little bit about what's changed in the core. So the processors, we talk about front end and back end usually. One of the things that we did to the front end was to add what's called a decoded micro-op cache. For those of you who are familiar with microarchitecture, we actually had something like this in the beginning of Pentium 4. It has value. And when the core family was created, that was switched for more powerful decoders. And now what we've done is we have both powerful decoders, instruction cache up front. We now have added a slightly different version of the micro-op cache back in. That allows us to run the decoders turned off frequently. Why does that matter? Decoders chew up a lot of power. So the power savings that we can get in the core is due also to this ability to have the cache and the micro-ops. The new additions to the memory cluster, we added 2 load store ports rather than the 1 load and 1 store that we had before. This means we can get more data into the CPU faster than we could before. More data in, more data out. Okay? We rebuilt, there we go. We rebuilt the core execution unit, the out-of-order engine. That was required because we added the AVX instructions. We needed to be able to have the data path 256-bit wide. Some increases to the physical register file, and a lot of work on the power efficiency of the circuits as well. Nowadays, if you go back a couple of years, Intel and many CPU companies used to design CPUs to figure out, okay, I've got this great new feature, I want to add it to the CPU. And the architects would say, okay, how much space does it cost me, and how fast can I make it go? Or how much speed do I get from it? Now they ask those same questions, and they have to ask, and how much power does it consume? So power is a key design parameter from the beginning for all of our circuit designs. Okay, moving on, let's talk about the processor graphics. Okay. So those of you who are familiar with our graphics solutions will know that we've had an integrated graphics solution for a long time, but it's been integrated into the chipset on the motherboard primarily. Okay? And then in the previous generation to this, we integrated it onto the onto the package, so that we had both the CPU and the GPU put together in the same package, but they weren't connected directly like we have here. Now they're connected directly on the die. As you saw in the previous diagram, they share the L3 cache. Okay? That means that they can communicate through the L3 cache rather than communicating over a PCIe bus. Okay? Now, what are some of the enhancements? Not only did we bring it in, we enhanced the graphics itself. We improved the energy efficiency significantly. Okay? Because we brought it off the chipset and into the die, that was a necessity. We added a lot of performance optimizations. Some of the things we did is we added a math box directly into every execution unit. For those who know some of the details, that is an important thing in terms of performance of the execution units that run the shaders. We added some fixed function capability. We're going to talk a little bit about that later for media, called Quicksync video. And then we optimized the circuit design and the layout because we put it into the same process. So it used to be that the CPU was on a process 1 or 2 generations ahead of where our integrated graphics was. Well, we might have 45 nanometer on the CPU, we might have 60 or 90 nanometer on the graphic. Now, because they're together, they by necessity have to be on the same die size. And so that makes it very much more power efficient and much more performant. Okay? How many people play games? How many people play games but don't want to admit it? Okay, and so with the second generation Core processor, we've got quite a large number of OEM partners that have systems out or soon to be out, as well as a large number of ISVs that we've been engaged with for some period of time. Generally, we work with ISVs 12 to 18 months in advance of a new processor. Okay, so I'm almost pretty much done with working on Sandy Bridge with ISVs right now. We're talking about the next generation processor with them already. Okay? Okay, let's dig in a little bit deeper. I don't want to spend a lot of time on this slide, but this is since you guys will probably have these slides afterwards, this is a good summary slide to describe the family. Let's dig right in. Okay, so how many people know what turbo boost technology is? A couple? Several? Okay, good. So, many years ago, you know that Intel implemented a technology called speed step technology. The idea being that we would clock the frequency of the processor down in order to save power. Okay? Well, starting with the last generation of processors, we figured out we could go the other way. If we have thermal headroom and we can shut off one or more of the cores, we can actually boost the frequency up. Okay? So why would you want to do that? Well, in some applications, might be very well multi-threaded. They'll benefit more often from the multiple cores, but then there are some applications that aren't well multi-threaded, and the developer may decide, I'm just not going to be able to do it, it's not possible, or not in the near future. Then turbo allows the CPU to boost the frequency up, and in many cases, boost the performance significantly. Okay? Now, what does the developer have to do to take advantage of this? Nothing. This happens automatically for them. Now, for some software, they might have to be aware of this, because they might be doing some really fancy things with paying attention to what the clock frequencies are doing. But for the majority of developers, it shouldn't be something that they have to worry about. Okay? Any questions? Does the graphic sort of make sense? The idea is, when you have all 4 cores running, you can boost a little bit. When you have only 2 cores running, you can boost quite a bit more. And when you have just a single core running, you can boost even more. Okay? Now here, to help solidify that, think about it. Back when we first started making multi-core processors, one of the reasons we said we could do multiple cores in the same package, in the same design, was because there's an exponential relationship between power and frequency. So if you remember back then, we would say, you reduce the frequency by 15%, you have the power output. Okay? So all you had to do was take one core that we had before, reduce the frequency by 15%, and then you can stick 2 of them next to each other in the same package, right? So that same relationship allows us, when we only have one of the cores running, we can actually boost this frequency significantly higher. Okay? Any questions? Okay. Okay, how many people transcode video? Really? More? How many people have video cameras? You save it on the computer, you ship it to your friends. How many people upload videos to YouTube or Facebook? It's kind of slow. And the process of uploading a video from your camera or your computer to YouTube does what's called transcoding. It decodes the video into its raw format and then re-encodes it into a different format, usually smaller, so that the bandwidth to communicate that upwards is significantly less, and so that you can upload into YouTube or Facebook significantly faster. Now, for a long time, we've had the ability to decode or accelerate the decode process in hardware. But whenever you had to encode, you have to do that in software. Okay? With Sandy Bridge, we've implemented, so that's what this shows up here. We would do that processing and encoding in software, and then in Sandy Bridge, we can now do all of that in hardware. Okay? That significantly speeds up the transcoding process, which translates into you being able to upload videos to YouTube or Facebook much faster. And generally, you're talking about a 2x increase in terms of performance for most software algorithms that do transcoding. Okay, and the technology behind that is what we call Quicksync video. I'm going to talk about how programmers take advantage of that in a couple more slides. Okay, so those people that talk about gaming, that play games, we think about gaming in a couple of different ways. We think about games as enthusiasts, mainstream, and casual. Okay? Now, I told you that we brought the GPU directly into the CPU, right? And we can play games better than we used to before. But when we do that, we're specifically targeting mainstream and casual games. Okay? While we've integrated the GPU into the CPU, it still doesn't have the same performance as a 300-watt, 500-euro graphics card. You know, we're pretty good, but we can't make magic happen. Okay? So when you talk about Core i7 and then the enthusiast crowd, games like Crisis, Battlefield 3, etc., those are still going to use pretty much discrete graphics cards. Whereas when you look at World of Warcraft, Farmville, and similar games, those will run just fine with the integrated graphics on the CPU. Okay? And this is just showing some of the performance compared to where we are. Sandy Bridge has two SKUs of graphics. There's a 2000 and a 3000, depending on whether you have a higher-end system or a slightly lower system. Compared to a previous generation, there's a significant boost in graphics capability. Now, one of the things that I think is really cool is when we talk to software developers, we haven't had the best reputation in the industry with our integrated graphics. And most of them said, I don't know. I don't think it can work. And what we found over the last year when we brought Sandy Bridge to them is that they were completely stunned by its capability and were really excited to support it. Okay? And some of the industry's most harsh critics about our graphics have turned around and are cautiously optimistic about our capabilities. So I think that's a big step forward. Okay, AVX, Advanced Vector Extensions. So AVX is a set of extensions. It's kind of a follow-on to SSC4. The main characteristic of AVX is that it's double the size of SSC4. So in SSC4, you could process 4 things in parallel, basically. In AVX, you can process 8 things in parallel. Okay? So theoretically, you can process twice the amount of items as you could before. Now, you're not going to get a perfect 2x speed up because of some other things like getting the things into the CPU, etc., memory bandwidth, your particular algorithm, etc. But we've seen anywhere from 1.2 to 1.5x improvement in performance by using AVX. And I think this afternoon you actually have somebody coming to talk about their experience with AVX as well in their commercial software. Okay? Okay, so what do programmers have to do? Well, let's take a little humor break here first.